All right, let's come back for discussion. And now, this vector formulation of rotation is actually beyond the syllabus. But I just want to include this section for two purposes. The first purpose is that I want to make everything complete. Now, in the derivation of Newton's second law for rotation in terms of the angular momentum, we put the moment of inertia inside the time derivative, right? And we do it without reason. We haven't proven that it can be done like this, okay? Because when the moment of inertia does change with time, that equation is no longer trivial, because the time derivative also may act on the moment of inertia. So there's no point for us to assume that will work. And we now will present the general proof. Now the general proof is a little bit more abstract, but it shows you the power of using mathematics. You couldn't have imagined that it's true if you don't rely on mathematics. Okay, there's no way for you to use a physical intuition or whatever physical picture to think about this result. You only have to rely on mathematics. That is the only way to physics, in fact. And in this case, I just want you to present you this beautiful proof to show you that why you have to rely on mathematics to arrive at this result. And this result is very beautiful mathematically, but you cannot use your mind to think about the physical intuition, think about the picture, you cannot arrive at. Okay, so that is the idea. But I will not test it in the final exam. Don't worry about this. So let's start with the vector formulation. Now, people ask me if rotation is a vector. The answer is no, rotation is not a vector. Why? Why no, rotation is not a vector? By rotation, I mean a finite angle rotation. Now, suppose I have a book, okay, and I arrange the three axes in this way. This is x-axis, z-axis, and the y-axis. The y-axis is now perpendicular to the large surface of the book. Okay, now so we make a rotation about the x-axis and the y-axis by 90 degrees, but we can do it two ways. The first way is that we first rotate about x-axis. The x-axis is this axis, right? So when we rotate the whole book about the x-axis, the robot turns like this, right? This is the x-axis. So we turn the book like this. So now we have the front page of the book facing us, okay? After rotating about x-axis by 90 degrees. Then we rotate about the y-axis, which is the vertical axis. So we rotate about it 90 degrees about the y-axis. So the side of the book, the back side of the book is now facing us. Okay, so is that okay? First we rotate about the x-axis, and then we rotate about the y-axis. That is the first kind of rotation. The second kind of rotation is we simply reverse the order. We first rotate about the vertical axis, that is the y-axis first. So after we rotate about y-axis, the book becomes like this. And then we rotate about the x-axis. The x-axis is this axis. So we rotate about the 90 degrees. We have the book, the front page of the book facing us, but the book is not upright. The book is tilted by 90 degrees. Now, so obviously these two cases are not the same. Now, but these two cases in both of the situation, we have rotated the book about two axes by 90 degrees, but the order is different. For the first case, we first rotate about the x-axis and then rotate about the y-axis. But for the second case, we rotate about the y-axis first and then the x-axis. And it turns out that the two results are different. Now, if you consider the rotation to be vector, you will run into difficulty. Why? Because the addition of two vectors is commutative. Okay, that means when theta x is added to theta y, it must be the same as theta y x added to theta x. The addition of two vectors should not depend on the order of the two vectors. How do two vectors arrange? Which vector go first does not matter. So if you consider the vector, the rotation as a vector, these two examples means that if you reverse the order of the two vectors, if you reverse theta x with theta y, then they will produce different results. So that means the finite rotation cannot be treated as vector. They are not vector at all. Now, but it happens that this is very strange, but you have to accept it. We skip the proof. If you imagine there's an infinitesimal rotation, the rotation is very small. It rotates by about certain axis by a small angle d theta. And if we count everything to the first order of that d theta, you will find that rotation about different axes, they will commute. D theta x plus d theta y is equal to d theta y plus d theta x. As long as the angle is small enough and you count all the quantity to the first order, you will find that they commute. And so the differential rotation, but not the finite rotation, is a vector. And if you divide it by dt, you get the angular velocity. So the angular velocity is also a vector. That is a secret. Now, although a finite rotation is not a vector, but the angular velocity is a vector. Infinitesimal rotation and the finite and the angular velocity, they are vectors. So we can use a vector to denote the rotation by using the angular velocity. Now, as we say, if I use my right hand, my forefinger rotate along the linear velocity direction, it's curved like this. So the particle rotate like this. The direction of my thumb is the direction of my angular velocity. Okay, so the omega is now in the upward direction, meaning that actually the particle curve around the axis like this. Okay. Now we want to prove about this relation. The linear velocity and the angular velocity, they are of course related by in your high school study, V is equal to omega r pro, right? But now I want to prove a general relation. V is equal to omega cross r. There's a cross product here. Now, why is there a cross product? Imagine now we measure everything, the position of the particle from a point O along the axis of rotation. So the position of the particle at any time is given by this position vector r. The velocity, the linear velocity of the particle is tangential to the circle. So it in the tangential direction. Now, imagine the omega is now along the axis. So omega cos r, what is the direction? If you have a omega in the z direction, vertical direction, and you cos with r, the position vector to the particle, you got a v vector that is in the tangential direction. So the direction is right. Okay, so the direction of v is actually in the direction of omega cos r. Now we check the magnitude. How about the magnitude? The cross product between the omega and r, the magnitude is equal to omega r sine theta, where theta is this angle, right? That is the definition for the cross product. But notice that, what is r sine theta? R sine theta is the perpendicular direction. Now, r is this vector. And this is a right angle triangle. So r sine theta is actually the distance, the perpendicular distance of the particle from the axis of rotation. And this is of course true because r sine theta is r pro, the perpendicular distance. So the equation simply produce the equation you learned in high school. The linear velocity being equal to the omega angular velocity multiplied by the perpendicular distance to the axis. Okay, so V is equal to omega r pro. Okay, where r pro means the perpendicular distance of the particle from the axis. Okay, so again, we check the magnitude. The magnitude is also correct. So we can write V equal to omega cross r. And similarly, we can define the torque like using a cross product. Okay, the cross product is like this. If the particle is here, we apply a force in this direction. It makes an angle phi with the radial direction. Then we resolve the perpendicular component of the force. I call F pro. F pro R is the torque, right? That is by definition. But F pro in this case is F sine phi. And F sine phi multiplied by R is FR sine phi. That is the magnitude of the torque. Now we look at the cross product here. The torque is defined as R cross F. R cross F is actually the magnitude of R multiplied by the magnitude of F multiplied by the sine, the angle between them, that is sine phi. So the magnitude is correct, right? And how about the direction? The direction is also correct. You imagine the force act like this. So you have a perpendicular component in this direction. It tends to rotate the particle in the anti-clockwise direction about the origin O. But if you use your right hand, the particle rotate like this, the thumb will be pointing out of the page. And that is exactly the direction of the torque. And you can see for this cross product, R is outwards. You cross with F, you get a torque. That is exactly our page. And that is, of course, the correct direction of a torque. So the direction is also correct. Okay, is that okay? We can also define the angular momentum in a similar way. Now, the torque is R cos F. Originally, we defined F per multiplied by R, right? But for vector, we can define it R cross F. For angular momentum, the same things happen. Our original definition is the perpendicular component of the linear momentum P per multiplied by R, right? And we do it similarly as a torque. Now we define the angular momentum as R cross P, okay? It's also defined by a cross product. And P is, of course, the linear momentum mv, okay? Now, so we turn everything into vectors. If you believe that's this expression, if you believe that the torque is R cross F and the angular momentum R cross P, everything is turned into vectors. And now you're ready for the general proof of the law of Newton's second law in rotational form. Okay, and also they are fully presented in vectors. Now let's start with a single particle. This is the angular momentum. We define R cross P. So we want to find the rate of change of angular momentum. So we differentiate this. Now we differentiate this just like the product rule of a usual differentiation. Because R and P, they are the product, right? So we differentiate like what we are doing with the product of two functions. We differentiate the R first, cross with P, plus we have the R cross with the derivative of P. That is a product rule, right? But in applying the product rule to a cross product, we must be careful not to reverse the order of the two vectors. Otherwise, there will be a minus sign introduced into that equation. So in applying the product rule for a cross product, we have to keep the order of the two vectors unchanged. Okay, but that is simple. Okay, we only have to bear in mind that the order of the two vectors does not change, and we apply the product rule just like in the same way as we apply to the scalar product, the scalar quantity. Now let's take a look at this expression. Let's take a look at the first term. We have the R dt cross with P, but the R dt is a velocity, is that right? The differentiation, the time derivative of the position is of course the velocity, but the momentum is also the velocity multiplied by the mass, right? So we have the velocity cross with the velocity, right? The cross product between the velocity vector with itself. But the two vectors must be parallel, right? Because they're the same vector. If the two vectors are parallel to each other, the cross product is zero. Because cross product involves the sine, the angle between them. So the zero angle must give you a zero result. So this term simply vanishes. How about the second term? The second term involves the time derivative of the linear momentum. But by Newton's second law, the time derivative of the linear momentum is the net force. So this becomes the capital F, right? So this becomes R cos F. But so the time derivative of the angular momentum is R cos F, which is the torque we have just defined, right? So the torque now becomes the L dt. We have proven that. Okay, for a single particle, at least for a single particle, we have proved that. Is that clear? The derivation is actually very simple. It's not difficult. If you accept that the angular momentum and the torque can be expressed in a vector product, you just need a few lines of derivation to arrive at this result. Now, how about system of particle? This is more difficult actually, but you can manage to understand it if you are careful enough. Now, we form a summation of Ri cos Pi. Ri and Pi is the position and the linear momentum of the I particle. So for that particle, we have the angular momentum of Ri cos Pi, and we form a sum of all this quantity over all the particle, we get the total angular momentum. So that's a simple summation of the angular momentum of individual particle. We get the total angular momentum. Okay. Now we differentiated both sides before, and just like before, we just apply the product rule. We have the Ri dt cross with Pi plus Ri cross with the Pi dt. We just applying the product rule for differentiation, but to a cross product. The first term is 0 as before, because the Ri dt is just V. The momentum also contains a V, so Vi cross Vi is 0 as before, just like a single particle. For the second term, the Pi dt is the force acting on the I particle, right? By Newton's second law. Newton's second law states that Fi is the force is the rate of change of the linear momentum, right? So that becomes Fi. So you can see immediately the rate of change of angular momentum become summation Ri cos Fi. Okay, so Ri cos Fi is the torque, right? It's a summation of the torque acting on the particle I, right? And we sum over all the particle, we get the total torque acting on the system, and that is the rate of change of angular momentum. Now, but there's there's a problem here. The summation of all this torque also include the internal torque. When the particle interact with each other, now you can have an external agent affecting the particle, producing torque on them, but you also may have internal torque. That is when the particle interact with each other in a system, then they may exert torque on each other. So this torque also includes the internal torque, not just the external agent torque. So you have to separate the torque into two terms. The first torque, which has the superscript of E, is the external torque. The external torque acting on the I particle. I denote it as tau I with a superscript E. The E is not a power. It's just a symbol to denote this torque is due to an external agent on particle I. Now the second term contains a summation, which is a little bit more complicated. I call it tau ij. Tau ij is an internal torque due to the interaction of two particles. The particle pair I and J, they interact with each other. So the particle J produces a torque on particle I, and that is denoted by tau ij. Okay, the first index is the particle that's being acted, that is particle I. The second index is the particle that produces the torque. Okay, so tau ij is the torque on particle I due to particle J. And because we are talking about the total torque on the I particle, so we form a summation of all the internal torque acting on particle I due to all other particles. So we form a summation over J, that is the other particle. Okay. So now the torque is separated into the external torque and the internal torque. And the internal torque contains a summation over all other particles. Okay. Now let us put this equation back to the original summation. So we have a double summation here. Okay, because the torque the particle I can be written as this plus this summation. So when you put it back, the first term is a simple summation of the external torque. So that becomes the total external torque acting on particle, acting on the system. The torque IE is the total external torque acting on particle I. If we sum over all of the particle, that means the total external torque acting on the system. Okay. The second term is the double summation. Tau ij sum over I and j. And we are going to prove that this summation is in fact zero. Now this summation is actually very similar to what we have done for Newton's second law for a system of particle. In proving Newton's second law for a system of particle, we also consider internal force, right? Fij and Fji. And because they form an action reaction pair, Fij and Fji, they are equal and opposite. They differ only by a minus sign. So when we sum up the two terms for the pair, they become zero. The similar thing happens here. Okay, if you consider the pair of the particle I and particle j, the position are denoted by Ri and Rj. Suppose there is an internal force between them. Okay, the internal force form an action reaction pair by Newton's third law. So let me assume that the force Fij is the force acting on particle I due to particle j. And Fji is the force acting on particle j due to particle I. So these two forces, they form an action reaction pair. And they act along the line joining the two particles. Okay, so this is the internal force. Now, so let's see this summation. When you come, because the summation of over ij go over all terms, so you must encounter a term with tau ij. Tau ij is Ri cross Fij, right? And in the summation, you will also encounter the reverse, the term with the reverse index. You will also encounter a term with tau ji instead of tau ij. So you simply reverse these two index, and tau ji is Rj cross Fji. So that involves a pair of action and reaction, the force Fij and Fji. Let's see what happens if the two terms are summed together. If I sum up the two internal torque on these two particles, what I can see is that we have Ri cross with Fij, Rj cross with Fji. But since Fij and Fji are in action and reaction pair, Fji is equal to minus Fij. That is Newton's third law. Okay. So immediately I turn this Fji into minus Fij. And so I can pick this Fij out of the brackets. So the two vectors Ri and Rj, they subtract each other. And then I make a cross product with Fij. But you can see that the force actually acts along the direction between the two particles. Okay, the force actually acts along the line joining the two particles. So, and also Ri minus Rj is this vector. It also is in the direction along the line joining the particle. So the two vectors are parallel to each other, either parallel or anti-parallel. It depends on the sign. But either parallel or anti-parallel produce a zero result when the two vectors are crossed together. If you form a cross product between two vectors that are either parallel or anti-parallel, the result is zero. So the internal torque cancel in pair. The particle I and the particle j, they interact with each other, but the torque they produce on each other, when you sum up the two torque, they cancel in pair. So eventually, when you form a double summation over all the particles, all the internal torque will cancel. All the internal torque will cancel. So the internal interaction doesn't matter. And eventually, you will have a single beautiful equation of the rate of change of the angular momentum of the system being equal to the external torque. Now, for this equation, we simply skip any subscript or superscript. The torque here means the external torque. Okay, the internal torque doesn't matter. Okay, it only matters when you apply an external torque to the system. It may come from your hand, it may come from some friction, or it may come from any other body. But the internal torque between the particle inside the object, they cancel in pair. It does not appear in the equation. So that becomes very beautiful. And it is actually the most general form. It applies for arbitrary mass distribution moving arbitrarily. Okay, so this is a most general form. Even if you don't have a fixed axis of rotation, even if you are talking about a system of air molecule, a system of air molecule may moving randomly, they may not have a given axis of rotation. Even if you don't have a given axis of rotation and the particle are moving randomly, and the particle moving in a very complicated way, you can still apply this equation. So you see how powerful this equation is. Okay. Now, what we have studied is only the special case. For one special case, the body is rotated about a given axis. So the moment of inertia, so the angular momentum can be written as the moment of inertia about that axis multiplied by the angular speed. And in that case, you will have torque equal to the time derivative of I omega. And now, because this equation is general, L is defined in a more general way. So now L written in terms of I omega in this form, the time derivative also acts on I. Okay, I don't cheat you now. The time derivative can act on both I and omega. Okay, so that is a more general form of Newton's second law of rotation. Now I've proven that. Okay, this equation holds even for I change with time. That is for non-rigid body, like for example a skater. And even in this case, you may have the axis of rotation changing with time. That also holds. But I will not talk about this case. For the case of spinning top, the axis of the top will precess in time. That allows the spinning axis to also change with time. But I will not talk about that very general situation. So if the total external torque is 0, then the angular momentum will be conserved. And bear in mind that now the angular momentum is a vector. The vector is given by the right-hand rule. Okay. And when we are understanding phenomena about torque and angular momentum, we should always think about them as vector. Okay. I will skip this example because I don't have enough time to teach about it. Okay. Let us, if I have time, I will go back, but let's skip this example first. The gyroscopic precession is a little bit complicated. Now, we also want to address another question. In our discussion for an energy for rotating body, we separate the two terms, right? We separate the kinetic energy into the kinetic energy for translational motion and the kinetic energy for rotation about the center of mass. That is again not trivial. That separation is again not trivial. And we want to prove it mathematically that this is possible. The separation between of the two energies is possible if we are considering about the rotation about the center of mass and also the translational motion about the center of mass. Now we have a special case for this. Suppose we have a circular object. This may be, say, a cylinder, or maybe a sphere, or maybe a spherical shell, whatever is this. Suppose it's rotating about this axis, okay? And it also have a translational velocity in its center of mass. So the motion, okay, is actually the sum of these two, okay? Now, when we consider the rotation of the body about the center of mass, we have an opposite pair of particles. On each side, we have a mass m because the body is symmetric, okay? But because the body is symmetric about the axis of rotation, because it's center of mass, the object is circular. So we have a pair of particles and opposite side of the center of mass. And this pair of particles has the opposite velocity. One with velocity v in this direction, and the other with velocity minus v in opposite direction. Is that right? Now the body as a whole is moving with its center of mass, having a velocity big V. So the total velocity of this particle pair, for this particle, you have this big V added to this small v. So the resultant velocity is this, right? And for this, and for the particle on the opposite side, you also have the velocity big V for the center of mass added to the velocity of rotation minus v in this direction. So the resultant velocity is in this direction. Now you can see the two velocities are different. But if you consider the kinetic energy of this pair, you can simplify the situation a little bit. Now why? Let us consider the kinetic energy of this pair of particles. For the first particle, you have 1/2 m v squared, right? But the v is the total velocity. So it is the capital V added to small v. And after you add the two velocity, you get the total velocity and you square it. For the particle on the opposite side, you have big V minus v, small v, because the particle on the has an opposite velocity for rotation on the opposite side, right? So now you have a minus sign here, big V minus small v squared. Okay. Now let's expand the brackets. Big V plus small v squared is big V squared to big V dot with small v plus small v squared. But if you have a minus sign here, you would have big V squared minus 2 big V dot small v plus small v squared. You have a minus sign in the cross term, while you have the plus sign for the first term, right? So the plus sign and so this term and this term, they cancel. Okay, the cross term cancel if you consider a pair, okay, of pair of particles instead of single one. Okay, the plus 2v dot v cancel with minus 2v dot v. So we don't have the cross term. The result is simple. You simply have 2 times 1/2 mv squared plus 2 times 1/2 m big V squared. Now, so you then will form a summation because you can consider a circular object and being formed by many pairs of such particles. And for each pair of particles, you have a kinetic energy like this. Now you form a summation of the first thing. If you form a summation of the first thing, and if you have the small v expressed as r omega, then eventually, if you form a summation of all the particle pairs of the circular object, you eventually will reach a term of 1/2 I omega squared. Because summation mRi per square is the moment of inertia. And the omega, all the particles share the same omega. So the omega can be singled out. So now you have, for all particle pair, the term for rotational kg as 1/2 I omega squared. How about this? For each particle, you associate each particle pair, you associate a term of 1/2 mv squared, right? And you sum up all the particle, it just gives you the total mass, 1/2 the total mass, big V squared. And this is translational kinetic energy of the axis. Okay. So now you complete the proof. You can now separate the two, the energy in kinetic energy into 2 terms. One for translational motion and the other one for rotational motion. But that has to be done about the symmetry axis. Okay, the body must be rotating about the symmetry axis in order for this to hold. Okay, and the body has to be circular in this particular proof. Now, I will not show you the detailed proof because the proof is rather difficult. But I want to make a more general statement that the separation of the rotational kg and the translational kg, that will work as long as you take the rotation and the translational motion about the center of mass. It doesn't matter even if you have not a non-circular object. Even if you have an object of arbitrary shape, the separation of these two terms still hold. As long as you are calculating the kinetic energy of rotation about the cm, and you are calculating the translational kinetic energy of the whole body in terms of the cm, you can simply add up the two energy to get the total kinetic energy. Now, I will not show you the general proof. What I show you is a proof of a circular object. A circular object in which the object is rotating about the cm, and you can sum up the kinetic energy of the pairs of particles, and you arrive at this expression. But I told you that this expression is not that specific. It can be generalized to an arbitrary shaped object, but I will not show you the proof anyway. Now, but you should be very careful about the kinetic energy of rotation. Now, when we start our discussion of rotation, we think about an object rotate about a fixed axis. Okay, the object is not free to move around. It is simply rotating about a fixed axis, I call O. And the kinetic energy is simply given by half I omega squared. Okay, that is the total energy is simply the rotational energy, and I is the moment of inertia about the axis O, not about any other axis. Okay, now that is the kinetic energy for a body rotating about a fixed axis. Now our separation like this into two terms, what we are talking about is a body that has both rotational motion about the center of mass, and also center of mass is also moving. That is a free body. Okay, the free body is now has two motion. One is the rotation about cm. The other motion is the center of mass moving in space. The whole body moving in space, that is. And in that case, we can separate the kinetic energy into two terms. One for rotation and one for translation. Okay, now look that the two cases are different. For this case, it's rotating about a fixed axis. There's no translation. For this case, the body is free. It has both rotation and also it has a translation about for the center of mass. The center of mass has motion. Okay. Now there's a temptation. Somebody in the examination write the kinetic energy for a body rotating about a fixed axis in this form, half mv squared, where v is a center of mass position. But this is wrong. This equation cannot be carried over to this situation. Okay, when you are talking about the rotation about a fixed axis, you always have to use half I omega squared. You cannot take the center of mass position and measure its velocity and say that the kinetic energy is half mv squared. That is a mistake. Okay, so that will not work. Now, for vector formulation of rotational dynamic, if you are not clear about, if you want to see more, you are welcome to look at this e-learning module. Okay. So we have done with this chapter.